Welcome to the lecture on strain hardening and strain edging. So, again we are going to discuss about very two important strengthening mechanism in metals, and that is strain hardening as well as strain edging. So, strain hardening, as we know, it is an important industrial process used to harden metals or alloys that do not respond to heat treatment. So, we have seen the flow stress curve, that stress strain curve, and in that as after the plastic deformation, when you see the region where the flow stress value goes on increasing, basically that is indicative of the strain hardening zone. So, for those materials where you cannot do the hardening by the heat treatment, that is maybe by transformation hardening or so, in those cases the strain hardening becomes an important process. And in this case, basically what happens that when you do the plastic deformation, in that case the dislocation density in the crystal will be increased by 2 to 6 orders of magnitude, depending upon the amount of deformation which is undergone by the crystal. And since there will be increase in the dislocation density, so that will be that leads to increase in the stress required for the plastic deformation. So, the sources within the crystal, such as like that of the Frank Reed source, they generate the new dislocations during the plastic deformation, and so your it is found that the shear stress required to move a dislocation increases with the increasing dislocation density. So, what has been seen that the shear stress required, that is to move a dislocation tau, it is found to vary with the square root of the dislocation, and keeping the constants we write it like tau naught plus a root rho. So, basically what happens that this tau is the shear stress to move a dislocation, and this tau naught, this is basically the base stress to move the dislocation in crystal, when there is no other dislocation. So, in the absence of other dislocation, then you have A again is a constant. So, as we know that when your dislocation density will increase, so its value will be ranging, you have different values, and depending upon the increase in the dislocation density, your tau value will increase. So, what happens that this equation basically will be deriving, will be discussing about the work hardening behavior. So, if the dislocation density will increase, then the tau, that is shear stress required to move the dislocation, will go on increasing. So, basically for a soft crystal, if you look at, so for a soft crystal we have talked about the critical resolved shear stress. So, critical resolved shear stress CRSS, for initiation of the plastic deformation. So, as we discussed that this is the critical value which has to be reached for the initiation of plastic deformation, and for a soft crystal which is very annealed one. Now, this value is close to the 0.5 meganewton per meter square. So, this is the critical resolve shear stress for a very soft crystal. Now, if A is taken as 10 Newton per meter. Now, in that case now depending upon the value of rho, now suppose you are taking for a annealed crystal. So, for annealed crystal, if you look at, for annealed crystal, basically rho is of the order of 10 raised to the power 10 per meter square. So, if you take this rho value of 10 raised to the power 10 per meter square, so if you see tau will be tau naught. Now, tau naught is your this is the value 0.5, and then A value is 10, and then this will be multiplied by 10 raised to the power 5. So, it is its root, this is 0.5 mega Newton. So, certainly into 10 raised to the power 6. So, it will be coming in the term of Newton. So, it will be if you look at this value. So, this will be 10 raised to the power 6, and this is 0.5 10 raised to the power 6. So, it will be 1.5 into 10 raised to the power 6. So, that will be Newton per meter square. So, it will be 1.5 mega Newton per meter square. So, you see that this is a very small value for the annealed crystal. If you take heavily worked crystal, if you do the heavy working, in that case this 10 raised to the power 10, it can go up to 10 raised to the power 14 per meter square, or sometimes maybe many a times we talk in terms of per mm square. So, it will be divided by 10 raised to the power 6. So, if you take for heavily worked crystals, now in this case your rho becomes 10 raised to the power 14 per meter square. So, if the material is heavily worked, now in that case if you find the tau, now tau will be A. So, that will be tau naught is anyway 0.5 mega Newton. So, this is again 10 to the power 6 Newton per mm per meter square, plus A we know that it is 10, and then its root will be 10 raised to the power 7. So, basically it will be 100 into 10 raised to the power 6. So, it will be move 100 plus 0.5. So, it is close to 100 mega Newton per meter square. So, this way what we see that your dislocation value will be changing quite high when your dislocation the shear stress required to move the dislocation value, that will be changing, and that indicates the increase in the strength of the material. So, suppose you may deal with some questions like you have we are talking about, suppose the yield stress of a crystal. So, if we say that the yield stress of 1 mega Newton per meter square of an annealed copper crystal. Now, if that is increasing, so if that increased to 100 mega Newton per meter square. Now, so on cold working, so because we are cold working the material, so to a dislocation density of say suppose 10 raised to the power 14 per meter square. Now, in that case now if you are told that if cold working had been done to dislocation density of say 10 raised to the power 12 per meter square, now yield stress will be what? So, such kind of situation may come, you may face with that kind of problems. So, you can just use that formula, that is tau will be equal to tau naught plus a root rho. So, what you saw that when we are talking about the annealed crystal, so it is completely annealed without the absence of any dislocation. So, your tau naught is basically here given as 1 mega Newton per meter square. So, you can write that for this dislocation density of 10 raised to the power 14. So, this value has gone to 100 mega Newton per meter square. So, 100 will be 1 plus then you have A and under root, then dislocation density is 10 raised to the power 14. Now, in that case you require to find the shear stress to move the dislocation when your density dislocation density has gone to 10 raised to the power 12. So, what we see that certainly it will be lesser than this value, and you can solve these two equations and you can get the values. So, what you can from here you can say, so from this equation you will get that A will be 99 upon 10 raised to the power 7. So, you can use in this formula. So, tau will be 1 plus 99 by 10 raised to the power 7 into 10 raised to the power 6. So, it will be cut. So, it will be 10 here. So, 1 plus 9.9. So, it will be 10.9 mega Newton per meter square. So, this way depending upon the type of question, or you may have the question of different type. So, you can always solve the problems which you may face or you may come across of different type, and you can solve them with ease. Now, also if you try to see that what will be the effect of this cold working. So, when you do the when you increase the cold work, so if the degree of cold work is increased, so if it is the reduction by cold work, and if you do it in terms of percentage, and if you look at the property, then in the property basically changes. So, the tensile strength will be increasing. Similarly, the yield strength also will be increasing, and your elongation basically decreases, and also the reduction in area, that will be also is decreasing. So, this is elongation, this is reduction in area. So, this will be something like 10%, 20, 30, 40, 50, 60, 70. So, this is in terms of percentage. So, 10, 20, 30, 40, 50, 60 and 70. So, this way if you increase the reduction by cold work. So, in that case your this is the increase in its tensile properties or yield strength. So, this is tensile strength and this is your yield strength. So, a very as you know that a very common example can be cited for the use of the strain hardening process, that if you have a wire and if you try to bend it many number of times, then ultimately it breaks. So, basically what happens is that the dislocation density goes on increasing and the material becomes harder and harder, and at one point of time there is not at all any ductility or elongation. So, the material breaks. So, that way there is a fracture, you have brittle type of fracture to the material. So, this is the example of increase in the strain hardening because of the reduction. So, when you do the cold working, in that case you have the change in the properties or increase in the strength that is achieved. Now, we will come to the next the mechanism of strengthening, and this is strain aging. So, strain aging is usually associated with the yield point phenomena, in which the strength of metal is increased and the ductility is decreased on heating at a relatively low temperature after the cold working. So, what happens that normally if you talk about if you try to see the flow curve of a low carbon steel. So, we can have so what happens that initially what you see that you go the it will go to the elastic zone, and then after that it will go into the plastic zone. So, you will have a yield point observation, there will be yield drop, and then you will have the things the material will go into the plastic deformation zone. Now, what happens that it was seen that when basically you are you are unloading it and then further reloading it, then in that case that the serrations which you are seeing or the yield drop which you are yield point which is appearing, that normally is not seen. So, if you are once you have done and then further you have unloaded and further reloaded without much of the delay, in that case you do not see the appearance of yield point. However, again if you unload it and then you are edging it at some low temperature range, and then if you are further so after this treatment if you are further putting it under loading, in that case there is seen that there will be further appearance of the yield point, and then there will be yield drop basically, and then what you see that there is a decrease in the ductility also observed. So, that is basically the process of process of strain edging. So, this edging treatment basically will lead into certain traits, certain other observations are observed. So, that we can see by looking at the the stress strain curve for a low carbon steel. So, what was seen that if you have if you look at the stress strain curve for the low carbon steel. So, initially when you strain it, so it will go and then you will have this lead point observation, and then you will have further increase that will be observed. So, this will be your stress and this will be strain. So, this specimen is plastically strained through the yield point elongation, and initially it is strained to say suppose point x. So, we have after the yield point we have a strain to point x, and then after this point what we do is specimen is further unloaded. So, we are unloading this this specimen. Now what we do is we try to further reload it. So, so it is retested without any appreciable delay. We are not doing any delay and we are further retesting. Now, if you further retest, then it will go and then further it will go from here, and you will have this kind of the stress strain curve. So, what you see that once you do the reloading, then the yield point does not, the yield point which you have seen in the earlier case, now that does not appear this time, because it is seen, it is expected that and what is has been found that in this case the dislocation which is they are thought of being torn away. So, they are torn away from the atmosphere of carbon and nitrogen atoms. So, for that this yield point is not observed in such case. So, if further suppose say you go to this point y, you are straining, and then now again what you do is you are unloading it, and then you are further. So, you want to reload it after many days of aging, and if you do the aging, aging temperature may be the room temperature, or it may be up to 400 Kelvin of temperature. So, it will be something like 120 degrees centigrade. So, if you do the aging for many days, and if you do the further testing, then what you see that further you will have the increase in the yield, and then again you will have this yield point occurrence. So that is further seen. So from y to you are now going to z. So the yield point is further reappearing. So that is a reappearance of this yield point, and this is because of the diffusion of the carbon and nitrogen atoms to the dislocation. So in that region of aging, when when you have done the age, so during that aging period, this is because of the diffusion of the carbon and nitrogen atoms into the dislocation, and they are forming the new atmosphere of interstitials which will be anchoring the dislocations, and because of that again your appearance of yield point is observed in this case. So that is what is known as the strain aging, and the specimen is strained plastically beyond yield point elongation, further unloaded and retested without appreciable delay, then yield point on reloading does not appear. That is what we have seen, that when you first go to point X, then you are unloading and then reloading without much of delay. So you do not see any yield point elongation and yield point phenomena. So but when you go further, when you do the aging, in that case so once you go to point Y, then you unload and then reload it after some time of aging, normal aging at room temperature or somewhat higher temperature, then in that case again the yield point phenomena is observed, and in this case this is basically because of the carbon and nitrogen that diffusion into the dislocation during the aging period to form new atmospheres of interstitials anchoring these dislocations. So in this case what has been found, that it is found that this nitrogen is playing important role in the strain aging of iron than carbon, because of the higher solubility and diffusion coefficient of nitrogen as compared to carbon, and also it produces less complete precipitation during the slow cooling. So because of that, this nitrogen is considered to be more important than that of the carbon in that case. So basically it is very important to avoid this strain aging, especially when you go for the phenomena like deep drawing. So in those cases, if there will be reappearance of this yield point, in that case that may lead to the improper surface finish, because there will be because the reappearance of the yield point, so that may lead to the marks on the product. So these marks they are known as the stretcher strains, so that is observed. So basically normally we try to avoid this. So for controlling this strain aging, normally we try to have you have to control the amount of carbon or nitrogen, and for that many a times we try to add elements which can form carbides or nitrides, so that they can precipitate out. So that way you can avoid this phenomena of strain aging. Now it is very difficult to have you completely avoid this strain aging. So in that case what industrially what they do is that normally you will have you have to deform the metal to point X by roller leveling or skin pass rolling operation, and then further so in that case up to this point X you go for the roller leveling or skin pass rolling, and then use it immediately before it can age. So you have not to give time for aging. So that is what the remedy is. Now so what actually the effect of the strain aging is that one is that it is increasing the yield point, and also it leads to the decrease in the ductility and also low value of strain rate sensitivity. So these are basically the effect of the strain rate sensitivity. Also because of the strain aging, you will have the serrations in the stress strain curve also. So this is known as the dynamic strain aging behavior. So if you look at the stress strain curve for for iron, so in the iron it is seen that when you do at room temperature, your it goes like this. However, if you if you do the aging at different temperatures, in those cases what you see that if you do at 100 degrees C, so it will be going, and then you will have these strain these serrations observed. So this is at 373 Kelvin. So that is your 100 degrees centigrade. This is at room temperature. So this is that is known as so this is basically known as the Portable-Lee-Chatelier effect, because these are the scientists who have discussed about it. If you go to 200 degrees centigrade, so your curve will look like this, and then you will have again the serrations will coming up. So this is 473 Kelvin, that is 200 degrees centigrade, and at 300 degrees C it will be going like this. So it will be at so 300 degrees centigrade, or it is 573 Kelvin. So so ultimately basically you have tensile ductility is basically reduced in those cases. Now what is so this effect which is seen now in these cases, what we see that this effect basically is known as the Portable-Lee-Chatelier effect. So basically we can understand this from this point, that in such cases when you are increasing the temperature, suppose in this case 373 or 473 Kelvin, in those cases what happens that these solute atoms, they are able to diffuse in the specimen at a faster rate as compared to the movement of the dislocations, and so as to catch or lock them. So what happens that in that case the load has to be increased, and so that when the dislocations are torn away from the solute atoms, and so ultimately there is a load drop. So that is how dropping and then increasing that continues, that leads to the formation of these serrations. So that is not desirable in fact. So that is why what we do is normally we try to have such a condition, so that the effect of this carbon and nitrogen which is there, which shows which is responsible for the reappearance of the yield point, and also if you look at these serrations. So especially in those operations you will have to have a lower amount of carbon and nitrogen, or you will have you have to do these operations. Once you go to the region X, then you should finish that forming operation without giving the time for aging, or without much of the delay. So that way so what we see that this is also strengthening, it is increasing the strength. So basically strain aging is another way to increase the strength of the material. So that is that is about the strain aging. So we discussed mainly in this lecture about the strain hardening mechanism and also the strain aging effect. We will have the discussion about few of these topics and the question solving on these topics in our coming lectures. Thank you very much.